Let me introduce and say you welcome to the next session of the memoirs of the Academy of Information Studies. So I'm pleased to welcome Dr. Stuart Kauffman, a renowned biologist who will tell us, or well, will explain us a few of his views on his stay with Warren McCulloch, the founder of the modern AI. For some people, for other people, he is the person who actually developed the neuronal model, and he's a famous psychologist and well, physiologist in fact. So let me ask first Stu to introduce himself with a few words about himself. Everybody knows him, but nevertheless, maybe only a few words on yourself.
Well, Plamen, thank you. And I'm truly glad to have this opportunity for a conversation among us. There's lots of really interesting questions, and I'm curious to see what we will make of them. So I trained as a philosopher at Oxford, then became a medical doctor in San Francisco, and went into theoretical biology while I was in medical school. And I worked on things like cancer and the origin of life and economics and some physics. I've been a scientist now for slightly over 60 years. And I think that I've done so many references. I'm just going to make a big pot and randomly add references to future papers. Warren was truly transformational in my life. And he is transformational also in the development of ideas that go back to Kant, spin off of Hegel. There was an enormous reaction to Hegel with logical atomism and logical positivism and Principia mathematics, then to Wittgenstein, the first Wittgenstein in the Tractatus, and that's then coupled to Warren, McCulloch, and Pitts in the 1943 seminal paper, A Logical Calculus of Ideas Immanent in the Mind. Somewhere after that is the second Wittgenstein, Investigations. From Warren, we get modern AI, and we get its limitations. I think a fundamental thing to talk about is the current difficulty in artificial life of getting open-ended evolution, and the current doubts, which I think are deeply well-founded, on attaining general artificial intelligence in a syntactic computational system. And what do we mean by information and so on? So there's lots of issues. Plamen, how would you like me to get to this? I could start by saying how I became connected with Warren and the story leading up to that. Is that a sensible thing to do, or do you want
Yes, that makes sense. And your first meetings, I mean, we're interested in your personal impression, your first impression, and how were you introduced to each other? So that's interesting, curious point.
So I will tell you the story. I was at Oxford. I was a Marshall Scholar, 61 to 63. And so I read philosophy, psychology, and physiology. So I studied neural nets because the receptor fields were just coming in. And at Dartmouth before that, I'd studied symbolic logic. And I came back, I decided I didn't want to be a philosopher. I decided I wanted to be a doctor. I reasoned as follows. I said at Oxford, in order to be a philosopher, you have to be as smart as Immanuel Kant. I am not as smart as Immanuel Kant. Therefore, I will become a doctor. It's not a syllogism, right? I mean, I demonstrated my complete incompetence. So I did a year's pre-med work in 1960, gosh, what was it? 1963, 64, at Berkeley. I just did all my pre-med courses, and I took a course that changed my life. I took a course in embryology. If you've never looked at or begun to think about the stunning features of a developing organism, it's magical. You start with a fertilized egg and you wind up with a frog or a human baby. And it's just amazing. Along the way, we looked at the famous little flatworms, and we were told if you cut the front half off from the back half, a day later the front half will regenerate the back half, and the back half will regenerate the front half. And I too managed surgery, and it's true. And you look at it and you say, how can that possibly be the case? Which gives me the chance to tell you what the main problem in developmental biology and developmental genetics was in 1960. By then, we know about DNA. We were getting to know the genetic code. We knew that a gene somehow encoded a protein. And we knew that all of the cells in an organism had the same chromosomes, so the same genes. And as I said, we knew that a gene somehow encoded an RNA that made a protein. The problem was that different cell types made different proteins. So red cells make hemoglobin and white cells make antibody molecules, but they have the same genes. And nobody knew how that could possibly be true. So a major discovery took place in 1961. Two French, all of this is going to tie in everywhere. Two French microbiologists whose names you know, Jacob and
Monod.
Jacob and Monod, discovered that in E. coli, one gene can make a protein that diffuses in the bacterium and binds the DNA adjacent to a set of 3 genes and shuts off the transcription of those 3 genes into RNA, so also blocks the translation of those messenger RNAs into proteins. In short, one gene can make a protein that turns another gene or set of 3 genes off. It's the famous lactosoperon. They later got the Nobel Prize for that. And just as I was coming back from Oxford, a few months before I got back, I think this is an article in February of 63, they published a seminal article saying, suppose you have 2 genes and A represses B and B represses A. Well, then you could have 2 steady states of activity, A on, B off, or A off, B on. And that in principle solves the problem about how different cell types can express different genes. So I read that in 1963. So this is my story, but it's an interesting story. So it was obvious. I was in medical school. I knew no physics. I knew logic. And I asked a funny question. And part of this, for all of us, is where do we get our questions from? Where did Warren get his questions from? It was obvious that there was, we thought at the time 100,000 genes. We now know there might be 100,000 now too. There's 23,000 protein coding genes. So it was intuitively obvious there's some network among a lot of genes turning one another on and off. And a sensible thing to do is to ask, so what's the actual network and how did it evolve? And that's exactly not the question I asked. I asked what seems to be a physicist's question, but I didn't know any physics. I wondered, is there some class of networks of light bulbs turning one another on and off that just typically or generically has the property that they behave with an enormous amount of order, so selection doesn't have to work too hard? So that's an odd question. So I approached it, this is going to get to me to Warren in a few years, by thinking I've got N genes, where N might be 10 or 100 or 10,000. And each gene is regulated by some genes. And I let there be a parameter K, which is the number of inputs to any gene. So I defined an NK ensemble where there's N light bulbs. Each light bulb receives exactly K inputs chosen at random among the N. So this gives an enormous wiring diagram. And then you have to give a rule to each gene saying what it's going to do. So an example is that if a gene has 2 inputs, so the gene is C and A and B are the inputs, an example of a rule is OR. C will turn on at the next moment if now A is on or B is on or they're both on. So that's the OR function. The N function is it'll only turn on if both of them are on. So there are 2 to the K Boolean functions of K inputs. So I wanted to assign at random a Boolean function to each gene on its K input. And that defines an ensemble, N light bulbs, K inputs per light bulb, to each light bulb assigned at random one of the 2 to the 2 to the k Boolean functions on k input. So I know how to design it. And I did a bunch of work with little networks, and I knew, in some weird sense of I was pretty sure that if k was 2, I was going to get spontaneous order. So this is all leading up to how I got to Warren Plamen, but it's pretty.
Sorry, is this the question that you really asked Warren to answer?
No, I'm going to tell you how. No, I answered it. I'm going to tell you how I got to Warren. So what I did is, before I knew Warren, I finally learned how to program in 1965 in Fortran. And so I wrote, with some help, my first program. And I wanted to randomize inputs and so on. To do so, I shuffled the last half of my deck. And I handed the deck into the guys at the counter, and they watched me shuffle the cards. And of course, they thought, "You're doing what?" But I didn't know I didn't know what Randex was. So I want to tell you the results I got. I was 25. I was paying for the computer time. I had 100 light bulbs. So that's 2 to the 100 states, where a state is all possible combinations of activities of the 100 light bulbs. So 2 to the 100 is 10 to the 30th states. Well, 10 to the 6 is a million. This is a lot of states. I have a clock. All of the light bulbs update synchronously, which means a state transitions to a state, transitions to a state. There's a finite number of states, so eventually it hits a state it's in before, that it's deterministic, so it goes around a cycle. I later learned it was an attractor. I'll call it a state cycle. So I handed in my deck, and I jumped into the state space about 1,000 times. And, an hour later, my little thing came back, and I was just stunned. I was 25, and the system had found one state cycle with 2 states on it, and 2 state cycles with 4 states on it. And that's all. So the system had localized itself to 4 plus 4 plus 2. It had localized its dynamical behavior to 10 states out of 10 to the 30th. And I was just stunned. And when I tell it right now, I still am. It blew my socks off. So I got initial results. I thought, this is order for free. There's something amazing going on. Then I got results analytically. If every light bulb has an input from every light bulb, so numerically, I got initial results that the length of one of these state cycles was the square root of the number of light bulbs. And the number of these state cycle attractors, if you jump in the net, how many of these state cycles is also square root n. But this was still for little nets. And I was just blown away. Well, I was in my 3rd year in medical school, and we were allowed to go away. I was at University of California in San Francisco.
I'm blown away too. I think something's got to be wrong with what you did.
No, nothing's wrong, Eric. It's been reconfirmed thousands of times.
Yeah.
Okay. No, it's true. It's known. It's a huge field now. To jump ahead, there's 2 main parameters in such a network. One is the number of inputs per light bulb. And now think of a Boolean function. If it's got k input, if you got k inputs, there are 2 to the k states of those inputs. So if there's 2 inputs, there's 4 input states. 0, 0, 0, 1, 1, 0, 1, 1. And for each of those 4 states, the Boolean function can be 0 or 1. So there's 16 Boolean functions, 4 inputs. So think of the Boolean function. It can have all zeros in it. The thing's always off, or all ones, all on. Or it can have 1, 1, and 3 zeros, or the reverse. So you can characterize the Boolean function by the fraction of ones in the Boolean function. So just call that P. So in a parameter space with K on the x-axis starting at 2 and P on the vertical axis with a mean value of 0.5, but going from 0 on the bottom to 1, there's a one-dimensional line symmetrical around the point 0.5, and it separates ordered behavior near the boundaries and chaotic behavior in the interior. And the one-dimensional locus is the phase transition where you get critical dynamical behavior. This is all now completely well established. accomplished. It took years. I had made networks with two inputs and a random choice of Boolean function, so P's 0.5, and that's critical. So I made from the start critical dynamical Boolean networks. Eric, what's remarkable about your responses, I found this when I was 25, and that was 60 years ago, and I published it a few years later, and there's a lot of physicists who still don't know it. We all know spin glasses and Curie temperature stuff. Why we don't know this 60 years later, I don't know. Meanwhile, if I think of a cell type as an attractor, like Jacob and Monod did, one cell type is A on B off, the other cell type is A off B off, then I can think of cell types as the different attractors, and I could do things like try to predict the number of cell types in an organism as a function of the number of genes, and it predicts a power law. Well, I was very excited. I wonder who in the world could possibly understand what the hell I'm talking about. So I'm a beginning third-year medical student, and I just wrote Warren. I thought maybe Warren McCulloch is famous. And I got back this most amazing letter. You have to picture you're a third-year medical student, and you're up in the morning doing stool guaiacs, which is take stool and you stain it to see if there's blood in the stool. And I got a letter from Warren. Here's his letter. Dear Kauffman, all Cambridge excited about your work. Well,
Wow.
that was pretty neat. I thought, wow. So much encouraged, I said, Professor McCulloch, I can come in the spring term, in the winter term for 3 or 4 months and study with you at MIT if you'll have me as your student. And Warren wrote back and he says, of course, come bring your young wife and live with us. So I thought, wow, this is fantastic. So Lizzie and I drove from San Francisco, kind of through the snow, and we arrived in Cambridge at Warren's house, and it was a foggy evening with snow on the tree. I just wanted to give you the set. So we're looking for his house, kind of wandering across lawns in the fog, the snow, and I knew what the man looked like, but he came out with a long beard looming out of the fog, and he said, Kauffman. I said, Professor McCulloch. So he ushered us into the house where it was warm, and he got on the phone within 2 minutes to Marvin Minsky. And here's what he said. Marvin, Kauffman's in town. I thought, wow.
Amazing.
Minsky truly didn't care at all. But I thought, when Warren talks, the world, whatever. So it was just wonderful. And then we met Rook. So we lived with them for 3 or 3.5 months. But other people had before. Something like 7 years before, my future chairman, Jack Cowan, a mathematician, and his wife, Jill, lived with Warren and Rook for 3 months. And then 3 years before, a man who became my dearest friend, Brian Goodwin, and his wife, Pearl, lived with Warren for 3 months. And then Liz and I did. So they all became, all of these people became dear friends for the rest of my life. So there I am with Warren. And among other scientific things, I obviously knew about McCulloch pets. Jerry Letman was there at the time. Umberto Maturana was there at the time. What the frog's eye tells the frog brain. All of that was going on beyond receptor fields. What are reticular formations doing? There was an enormous sense of excitement. There was the early efforts to try to rule out neural nets. And there had been, McCulloch and Pitts had done their stuff. It is a feed-forward neural net. And McCulloch and Pitts proved in 1943 that if you have a feed-forward network with n binary variables in each layer, feeding into the next layer, you can prove that in general, such a network you go rank from the front to the back, can compute any Boolean function on the input row. And that is the logical ideas of ideas immanent in the mind. So let's get to that. Can we pause here, Plamen, and say where Warren got that, or should I go on with Adventures with Warren?
Yeah, It's amazing. I mean, at that time, it appears to me, I mean, this story has obviously become your leitmotif for over 60 years.
Yeah,
Since that time, I mean, you have asked the same question all the time. And what is another story that's amazing to me is that probably Varela and Maturana's model, I mean, ideas emerged almost simultaneously, and also the ideas probably from about the game of life,
yeah,
the
yeah,
mathematician,
yeah,
yeah.
yeah. Conway, yeah, everybody was fiddling around. So
Yeah,
let me
it's
yeah,
similar. They all had encounters with computers and computer models, and they began working with them. And the amazing capability of these digital devices in
well,
modeling
Plamen, it
were.
was overwhelming. You know, I found myself calling the computer the macroscope. Um, so just let me tell you the results that I got while I was at MIT with the help of a brilliant graduate student. I was able to get up to 8,000 light bulbs. Here are the results. And I wound up publishing it with Warren in 67. I said, Warren, should you be on the paper? He said, as you wish. It might be useful for you. Was that sweet?
Yeah.
Okay. So,
Of course.
of course, I wanted him to be on the paper. So I have a McCulloch number of 1. McCulloch doesn't realize that he has a Kauffman number of 1. But anyway, it's a symmetric relationship.
Was that your first paper,
No, it's
Stuart?
my second paper. I'd published a
Second.
paper.
Okay.
I'd published a paper before that trying to explain cell differentiation by differential activation of sister chromatids by changing orders of replication. This is my second paper. Anyway, here's the results that I got, and it finally got published well in my paper in 1969 in the Journal of Theoretical Biology. And it took 40 years for that paper to get much attention. It's kind of fun looking at it. Here's what I found. The average length of one of these state cycles, the number of states on it, scales to square root n. N's the number of light bulbs. That's now a theorem that Nobel laureate Giorgio Parisi and his colleagues proved years later. Numerically, the number of attractors scales as square root n. Well, just pause. That meant I should be able to predict the natural cycle is the cell cycle, and the number of attractors should tell you something about the number of cell types in an organism with that many genes. And it worked. So I was able to plot cell cycle time in organisms as a function of the number of their genes, and the theory predicts it correctly. And I was able to plot the number of cell types in an organism as then known as a function of the DNA per cell, and it fit. That's pretty stunning. I
Absolutely.
felt, yeah,
Absolutely. I
it is
can
amazing.
imagine.
This is 1969. So meanwhile, I found some other things. Think that you're a state cycle, 10 states long, and if you got 100 genes, for every state, there's 100 bits. You can flip each bit to the opposite value. So there's 100 one-flip mutants of each state, and there's 10 states. So there's 1,000 states that are one Hamming step away from all the states on the state cycle. Well, I did the other opposite. I did that, and I asked, if I perturb you from this state and this state on, say, state cycle 7, you come back to the same cycle. You do 80% of the time. So you've got homeostasis for free. Cell types are stable and discretely different from one another, which they are. But if you leave, if there's 40 state cycles in the system, from any state cycle, you only go to a few. So there's restricted direct reachability, and that predicts that cell types differentiate into only a few other cell types directly. And that's true. And then it's true that any cell type can reach a lot of others along indirect paths. And that's true. And it predicts, the networks show the property that as you approach the attractors, the states become much more similar. And that if you take all of the state cycles, there's a set of light bulbs that are in exactly the same state on all the attractors. That predicts that there's a set of genes that are in the same state of activities on all the cell types. So that turns out to be true. I think there's some other things. Meanwhile, we discovered over the next years, we being a bunch of physicists, this is another romantic story. I was in Jerusalem with Gerard Weissbusch and his then wife Francois Vogel Sully, and they had made a random Boolean net. They're now called Kauffman nets. Anyway, maybe I'll call it the Kauffman model. They'd made the Kauffman model on a two-dimensional lattice, making it folded into a torus. So there's no bound. It's got periodic boundary conditions, and every light bulb has two inputs and two outputs on that lattice. One has inputs from the north and south, and outputs east-west, and the nearby ones reverse that. So it's a perfectly good two-input network. And what it allowed you to do is to see which light bulb were in what states. And they discovered something that was just beautiful that I could kind of see in my simulations. They discovered if you cut that torus open and laid it out to be a rectangle, color light bulbs that fall to a fixed state. You start the network and run it, and some light bulbs start changing. Color them red.
Mm-hmm.
Color the light bulbs that keep changing green. Or color a light bulb green if it can be in a different state, like in a different state on the different attractors. So the red guys never change on attractors, and the green guys can be different. And you see something amazing in these nets. You get a percolating red structure and isolated green islands. And I looked at that and I said, my God, look at that. There's got to be a phase transition as you tune parameters where this red thing, the green thing does not percolate, or it does percolate. And I saw that in 1985 on my sabbatical. And I gave a little lecture on it at the Hadassah Hospital. And I said, it's got to be true that as you tune parameters, the frozen component will be invaded by a growing set of green twinkling islands. When the green islands are just starting to percolate, you're going to get the most complex dynamical behavior. And so I realized that, and I gave a lecture on it, but I didn't write it up, which is kind of dumb. But I told Gerard and Françoise, and I gave a lecture at it in Hadassah in the summer of '85. Well, part of the reason I didn't write it up is that I went with Gerard as part of my sabbatical to Paris, to the École Nationale Supérieure, and brilliant Bernard Derrida, Jacques Derrida was there, and Bernard was just proving that K2 input nets are at a phase transition between order and criticality, and he proved a theorem, and I bet him he was wrong. And we went over to Rue Mouffetard, and I had to buy the bottle of wine, which was okay. It was good wine. They made the annealed model. I would have never done that. You had to be a physicist, and no geneticist would do it. So Bernard made a network in which you've got a network. You keep the same light bulbs. At every state transition, you rewire the network in terms of who's input to whom, and you rewire the network in terms of what the Boolean functions on the nodes are. So you have an infinite rank of these networks. It's called the annealed model because the network's not fixed. But the following is true. Take two different, just take two copies of this annealed network and start the two copies in two different initial states. If over time those two states ever become the same state, they always stay the same state forever. So what Bernard and later another colleague proved is that for two input networks, all the states ultimately converge onto a subset of states. They didn't estimate the number of convergent states, but it's got to scale a square root n. They might have done that by now. But if you had three input networks, they didn't. So there was a phase transition, and if you had one input networks, they did converge. So there's a phase transition between some kind of ordered state and some kind of chaotic state at k equals 2. That was later generalized with a p parameter. And that gives rise to this critical eye that separates order from chaos, and it's all established. To jump ahead a long time, it became obvious to ask, so are genetic regulatory networks at this critical boundary, which can carry out the maximum computation? And they are. 50 years later, we know that genetic regulatory networks are just slightly subcritical in yeast and in many, many other genetic networks. So we know that cortex is critical. So all of that grew out of all of that early stuff. It took till the mid-'80s to get that set of physicists interested. Meanwhile, no other physicists are interested. And 50 years later, some mathematicians are getting interested. So all that happened.
Let me ask you something. Were you discussing these ideas with Warren by that time already? Or everything came a bit later? I mean,
yeah, a lot of this came later, so I'm jumping ahead.
okay.
And just to tell you, for a while, it was thought that there were not very many genes, that most of the DNA was junk DNA. But it now turns out with the ENCODE product that it's not junk DNA. It's long non-coding nuclear RNA, and they're playing regulatory rules all over the place. So we have about 23,000 coding genes and somewhere between 25 and 70,000 of these other sequences. So your cell has the order of 50 to 100,000 polymer variables that are dynamically interacting with one another. And we came back later, a couple of years ago, Stefan Bornholdt and I came back, and it turned out that I had undersampled state space because of vast state space, and that if you sampled it, there was more than square root n attractors. And then Stefan Bornholdt and a woman, I'll remember her name in a moment, showed if you used asynchronous networks, you come back to square root n attractors. And it works. The theory predicts the number of cell type scales as a power law of the number of genes, and it does. We predict about a slope of 0.6, and the observed data is about a 0.75 or 0.8. So the theory predicts the right number of cell types. It predicts the stability of cell types. Everything, just the long run of this, is the paper flowered for about 5 years after I published it, then went quiescent, then the physicists picked it up in the mid-'80s, and then it was dead, and it finally started being quoted all over the place 40 years later, and it's now the standard view, or pretty much. Back to Warren. So there I am with Warren. He's just lovely. He thinks my wife Liz is really pretty cute, and Liz was very cute. And Warren would, this is not the dirty old man, it's just a man that's kind of aware of a pretty woman. They'd be talking to one another, and Warren would take occasionally a step towards Liz, and Liz would take a step back, and I'd see them in happy conversation, drifting along walls. Nothing inappropriate ever happened, but it was really sweet. Meanwhile, I have to tell you, right in the middle of this, I told you I would, Plamen. So Warren was very, very playful and very proud of being Scots. So here are 4 English declarative sentences. You ready?
Yeah.
It's going to be hard for you because maybe Eric is a native English speaker. Here it is. You ready?
Yeah.
In Paintaris, in Ognanis, in Marilzar, in Kleinanar.
Jesus, this is Gaelic or what?
Well, I've got a little Gaelic accent. I'll do it again and then decreasing Gaelic accent. He just kept smirking at me. In Paintaris, in Ognanis, in Marilzar, in Kleinanar. Now I'm going to get rid of the accent. In Paintar is, in Ognan is, in Marilzar, in Kleinanar. In Paintar is, in Ognan is, in Marilzar, in Kleinanar.
Jeez.
That's 4 straight English declarative sentences. Now, isn't it fun? Now I'm going to do it really slowly. Are you ready?
This sounds like like a koan. All these.
No, doesn't it? Yeah, well, and there was more than a twinkle in Warren's eye. It was sort of a feisty, you'll never get this. So here it is, very slowly. In pine,
Yeah.
there is.
Yes, there
In
is.
oak, none is.
Yes.
In mud, eels are. In
Okay.
clay, none are. Now I'll say it again. In pine tar is, in oak none is, in mud eels are, in clay none are. And you can hear it, right?
So
It's,
there is some logic inside all these statements, you know.
I don't know. Russell would have gone nuts. So meanwhile, there I am with Warren. And our relationship was such that I'd be in the bathtub, in the bathroom, and Warren would come in and sit on the toilet, and with the top down, and we would discuss for about an hour, what the implications were for different Boolean functions in the nets, and whether or not it had feedback loops or not, or one input feedback loops. Just on hour conversations that were in the bathroom, in the bedroom, whatever. And that's what he was like. It turned out, by the way, that I think I saw Marvin Minsky once. He didn't seem to respond to Warren's Kauffman's in town with too much alacrity. But Warren's style certainly had me blown away. Warren had a style of writing that was lyrical and brilliant. He started one paper saying, "We have no theory of knots." Well, he's right. We haven't classified all knots, I later learned. And what he was looking at is, you can talk about feed-forward networks where you network with feedback loops. Well, Kauffman networks were full of feedback loops because I randomly assigned things. So Warren found that all fascinating, and I did too. And, we just spent a lot of time talking about it. I'll get to some other personal things. Warren was then the president of the new Cybernetic Society. So I came and I gave a talk in parallel to one of my best friends from Dartmouth, Steve Grossberg, who I graduated third in my class and Steve was second. And so Steve was better than me. We're very dear friends after all these years. So Steve gave his talk on neural network stuff, and I gave my talk. And to my utter joyous vanity, it didn't matter that much. Anyway, I won first prize, and Stephen won second prize. So I got the Norbert Wiener Gold Medal, which I have and I enjoy. Then something was important in my life. I trained in medicine. Well, after I was Warren, I finished training in medicine at UCS in San Francisco, and it was the Vietnam War. I was against it. I even demonstrated again. That was another interesting event in San Francisco. About 20 students got together and we decided we would never fight in Vietnam. And we came out and we were above Golden Gate Park and looking down on the gate. And a carrier flotilla was coming in through the gate with a carrier, a couple cruisers, about 5 destroyers and five destroyer tenders or something coming through the gate. There's about 20 ships. And we looked down at that and we said, it's going to take a lot of letters. It did. Anyway, rather than being drafted, I could legitimately put off being drafted by doing something called a Berry plan, which allowed a doctor to do a residency in some field of interest, and you'd go into the Army at the end of your Berry plan. So I did a Berry plan in theoretical biology. I have no idea why the U.S. Army let me get away with a Berry plan in theoretical biology. Anyway, there I am with Warren, and being with Warren is part of my training in theoretical biology. And Warren looked at me and said, I don't think the U.S. Army needs a theoretical biologist. I said, Warren, that sounds like, now what? He says, I'm going to get into NIH. So Warren wrote something like the Secretary of the Army and something like the head of NIH and said, the Army does not need the best trained young theoretical biologist whatsoever. NIH does. So I was happy. I went to the National Cancer Institute for 2 years. After I'd gone to the University of Chicago, then I went to NCI, National Cancer Institute. So Warren was very helpful then. And another amazing thing happened. Jack Cowan had lived with Warren. Jack would become my first chairman, and Brian Goodwin had worked with Warren, lived with him. And one day I met Brian in Warren's office. He was about 4 years older than me, and in some profound sense, I just fell in love with him. I still am. He died about 5 years ago. Do you know the name Brian Goodwin?
Yes, sure. That's my next question. I mean, one of my questions is, how did you get together, all together, to these conferences at Komolek?
It was pretty magical.
Everybody of you were there, so
Yeah, we
you
were.
must have talked about that. So,
Oh, we did. I got there because of Warren, and I was doing a postdoc during my internship with a geneticist. I can't remember Alex's last name, and he was a fruit fly geneticist at the University of Cincinnati, and I wanted to study fruit flies because I wanted to look into transdetermination. So I was doing a postdoc. Oh, that's another fun story. You have to be a young doctor. I'm a young doctor. I'm on call at the hospital. I'm in my white coat with a stethoscope stuck in my pocket. You know, the way you're supposed to look. And I'm to give my first talk in the genetics department at the University of Cincinnati. And I'm about to walk on stage, and the nurse calls me and she says, "Dr. Kauffman, should we put this cardiac patient on a 1 gram or a half gram sodium diet?" This is not a big decision. So I said, "I don't know, half gram." But I didn't sound like that. I walked out and said, "Cardiac problem, we've got it under control." It was so much fun. Anyway, it was sweet. Anyway, so I give my first talk in Cincinnati. And in that, because of Alex's last name, I can't remember right now, Alex somehow got together with Warren, or Alex had been at the Waddington conferences, and with Warren, Jack Cow and Brian Goodwin were all there at one point, and they decided it would be great if I could come to these Waddington conferences, and they organized it and they got me invited. It was just truly wonderful. So I was a third-year medical student, and I was invited to Lake Como, to Cirbelloni, for the third and then finally the fourth Waddington conference. Waddington was just amazing. Do you know the name? Do all of you know the name?
yeah, sure. But that's what I'm amazed. So actually, you were the youngest of all the participants there.
I was.
Yeah.
I was 27. Yeah. Kate, both Liz and my present wife, Kate, chuckle at the picture. But what happened was, I got there, well, here's the background. Waddington through the 40s, the 30s, Waddington is Hal Waddington is the major figure. Start Darwin. There's two pathways from Darwin. One goes through the issues of blending inheritance, the rediscovery of Mendel's laws, the realization that Mendel's laws of atomic genes that don't blend could rescue Newton from blending inheritance, then the mathematics of population genetics with Fisher, Haldane, and Wright, which became population genetics, and it rescued Darwin from blending inheritance. But for population genetics purposes, the organism just doesn't matter. It's a box with some phenotype. So there's no organism in population genetics. There's just alleles and fitnesses. The organism came back into the story more. I don't know what's banging. The organism came back into evolutionary biology from Darwin to Waddington more than anybody else. Paul Weiss was important, but Waddington was central from the early 40s until his death. Wadd just became a hero. So he wrote a number of books in the 50s, The Strategy of the Gene, and so on. And he had the picture of genes interacting with one another in some kind of gene network, creating what he called an epigenetic landscape of flows among cell types,
Right.
looking kind of like a potential landscape. And it was a very powerful metaphor. But nobody knew what created these valleys and these pathways and these low points. So at the first Waddington conference that I was at, it was filled with really brilliant people. In particular, the mathematician René Thom was there, and he was developing category theory, and not category theory, catastrophe theory.
That's right.
And so Thom's view was that you could think of developmental biology as these different catastrophe. It's like the cusp catastrophe and the butterfly catastrophe. And I came along with random Boolean nets that had attractors that were distinct, that were stable to perturbations, and you could study mutations and it took over everybody's impression. So it was well received at the first Waddington conference, and at the second one a few years later. Some of the important things that happened is I made lifelong friends there. John Maynard Smith was one of the. So Dick Lewontin was there, Dick Levins, Brian, Jack, another, Christopher Longwood Higgins, Renee Tom. I was trying to understand what a Pfaffian was. It's a matrix of second order derivatives. So I made the mistake of asking Tom, and he said it's made up of jets of an infinite set of derivatives. Well, I was trying to figure out what is a infinite jet of derivatives, and what do you do with it? And basically, I didn't understand. But we did get to an important contest about making paper airplanes, and who could make the best paper airplane. And I made a paper airplane when I was 8, and I will confess it's a really cool paper airplane. But John Maynard Smith, after all, was an aeronautical engineer, so we had a competition about who could make a paper airplane that would fly furthest over the hedgerow, and I won by 4 feet. So that gave me a certain credibility, as you can imagine. Anyway, out of all that, people were interested in Boolean nets for about 4 years. Then molecular genetics came in for the next 40 years. And what people wanted to know is what gene makes what molecule that touches what gene. Interest in networks and their dynamics totally vanished for 40 years. Off on the side, the physicists in the mid-'80s came along and proved all sorts of results about criticality and what's called damage. If you perturb the activity of a gene, that can influence other genes. And at criticality, criticality is a little bit like the Curie temperature, where you get power law distributions. For a critical net, let me define it. The network's doing something. Flip some light bulb, color it purple. It's doing something different than it would have done. And after that, color any light bulb purple if it does something different than it would have done. So you get a purple avalanche. And what you get at criticality is a lot of small avalanches and not many big ones. And it's got a slope of, I think it's about -1. And if the system is chaotic, the avalanches are huge. They involve, a finite fraction of the light bulbs. And if it's ordered, you only get tiny avalanches. Years later, part of how we know that genetic regulatory networks are critical is that the geneticists in Toronto created 1,200 single gene deletions in yeast. And for each, they analyzed how many genes alter their expression patterns. And physicist friend Roberto Serra and his colleagues analyzed the power law, the distribution. It's a power law, and cells are just slightly subcritical, which is where we want them to be. Meanwhile, Sarah Walker and her colleagues at Arizona State have taken Boolean network models from about 100 known genetic nets. And you know the logic of the net. You can say, are you critical or not? And the answer is essentially they're all in this critical boundary. And they have something I discovered, which is why I thought 2-input nets would be good. Let me define a canalizing function. Take the OR function. I am C, and I have inputs from A and B, and the rule is OR. Well, if the rule is OR, if A is on, or if B is on, or both, I go on at the next moment. So it's guaranteed that if A is on, I'll be on at the next moment. A is a canalizing input. So is B. If B is on, I'm geared to be on at the next moment. So so A is a canalizing input, and B is one value of A suffices to determine what I will do, regardless of what the other inputs do. So you could define canalizing functions, and it's easy to see there's more canalizing, a larger fraction of the Boolean functions are canalizing with 2 inputs than with more inputs. It's turned out that criticality, the critical networks, are heavily biased towards these canalizing functions. So all of that kind of worked out. So we now know that genetic regulatory networks really are critical.
Mhm.
And since
Could
in
I just ask you one question? Did you ever
Sure.
get to know Eric Davidson, the developmental biologist? And
Sure,
his,
we were friendly enemies.
oh yeah, okay.
Well, Eric hated the idea of these sort of networks with feedback loops and everything.
Mhm.
He wanted his Britton and Davidson. Eric was really smart, and he did wonderful genetics in sea urchins. And they made a model roughly the same year that I did. It was basically hierarchical batteries,
Hmm.
like an army, and you had generals, and then each general controlled downseed batteries, and batteries could be controlled by more than one general. There's no feedback loops, but you had a sort of simple logic about how things would fire, and they wanted RNA to play important roles. That turned out to be right. There were no feedback loops in those nets,
Mhm.
but there were no feedback loops in Warren's nets either. Okay, they were feed-forward nets, and you can do a lot with feed-forward nets. Real genetic nets are full of feedback loops. But we didn't know that then. But it's perfectly well. In fact, there's a bias for self-inputs, also non-randomly. But yeah, he did brilliant work. It was
Did you
a
ever
very
did you ever get to debate him?
yeah. We were at a conference once in Berlin. It wasn't a debate; it was a discussion. I think we were something like friendly competitor, sort of enemies.
Mhm.
Well, he was a very smart guy, and kind of brooked no opposition, but very, very smart. Did you know him?
Yeah, I got to know him a little bit through my work on developmental biology, but yeah, I did meet him, yes, but briefly.
Yeah.
Stuart, let me ask you, because time is advancing. I would I would ask Pedro to, initialize new other talks, because there are so many interesting questions. You have been knowing so many interesting people. We are all wishing to learn more about them. But let me ask you one question that is puzzling me. All these war generation scientists you were in touch with, like Warren and also Norbert Wiener, Freeman Dyson, Alan Turing, all these guys. Also the physicists like Schrödinger, who actually moved later to biology, and of course also Francis Crick and Watson. So all these guys were, of course, knowing each other and communicating, but you were belonging to the next generation. I mean, the
Yeah.
of their scholars. So. Do you have the feeling that they were interacting between each other? So, in a way, for instance, that Warren sent you to the conference of Waddington, because Waddington was also from that milieu. They were in a similar age. I don't think that Warren was attending the
No,
conference. Of the common.
no, Warren wasn't part of that group in conferences.
Yeah.
Um,
But do you have
I,
the
so
feeling that
I,
they were building a kind of an academy? I mean, just like they were educating the next generation of, that you belong to. I mean, all these scientists, because there are so many ideas, as you said, Varela and Maturana were also belonging to your part, and their ideas came some 20 years later. I mean,
well,
even
yeah, Plamen, let me mention about Varela and
Mhm.
Maturana. I mean, I became a friend of Varela's and I met Maturana. They published that in 1977. In 1971, I published my first paper on the spontaneous emergence of collectively auto sets of peptides.
Right.
Okay, it's sort of so. I there's a story to my discovering the phase transition, first order phase transition to collective autocatalytic sets, and they are an example of what Maturana and Varela later published independently of autopoietic systems. So, we did it independently a few years apart, but they're basically the same idea, and much comes from that. So that part of it is, I could tell you the story. And anyway, part of the point is there has been a movement towards autopoietic systems, of which I'm actually an earlier example. I don't think Timur Ganti is, and Manfred Eigen isn't. Manfred almost is with the hypercycle. Timur Ganti is very good, but he's not got that. And the whole notion of autopoietic systems is fundamental. The very phrase says it. Autopoietic, it's poetic. It builds itself. It builds itself. And that's reached fruition in the last couple of years. Do you know this concept of constraint closure?
Yeah, of course. But
so that now fulfills rigorously the autopoietic idea that's sitting in Maturana and Varela, and constraint closure is largely due to Matteo Mosio and Mael Monteville. And it's a set of nonlinear processes and a set of constraints. There are boundary conditions, and the boundary conditions constrain the release of energy in the process to construct the same boundary conditions. And that's not in physics yet. It's brilliant.
But
and cells do that.
Do you have the feeling that somehow Warren was stimulating you, telling you, read this paper by Varela, or just to try to make the links between you from the younger generation? I mean,
it's the other, Plamen, it's the other way around. I was with Warren in '67.
Okay.
I invented autocatalytic sets.
Yes, that's
on my own in '71. 6 years later, independently, Maturana and Varela came up with autopoietic systems.
Yes.
And then we all met one another later. And I don't think there's much here. Our group on this call is much interested in information and questions about syntactic formal systems, propagation, whatever we mean by information. Living cells are physically embodied systems. They're not merely syntactic. They physically operate, they do work on one another. And part of what I'm hoping we'll talk about, and we did a few months ago, thank you. This is so important. Let me see if I can say it. The Turing machine is the ultimate machine. It's totally syntactic. It can carry out any algorithmic operation. An algorithmic operation, you could build a special purpose computer that did exactly that. Yeah, I would like to get across some ideas if I can. I don't know if we have time.
Yeah, take the time.
Yeah, I've discovered something about 3 months ago. I'm so puzzled by it, and we're all so into this information. Please forgive me. We've begun to really know one another. So I have been working on autocatalytic sets forever. Goran Ashkenazi has a 9-peptide autocatalytic set. He's in the Ben Gurion. And I'm going to define 3 terms. Please let me say these. See what you think. Okay? There's 9 peptides. Peptide 1, well, Gonan feeds in from the outside half fragments of each of the peptides. So this is going to be an open thermodynamic system. It's an open thermodynamic chemical reaction system. It's not a digital computer. What happens is that peptide 1 binds the 2 half fragments of peptide 2 and ligates them to make a second copy of peptide 2. But in doing so, peptide 1 is a boundary constraint, that ligates the 2 half fragments of peptide 2, so orients them in 3 space, so lowers the activation barrier to form peptide 2, and thermodynamic work is done to construct 2. Okay? Pause. What's thermodynamic work? It is the constrained release of energy into a few degrees of freedom. That's Atkins' definition. It's not just force acting through a distance. So think of the powder, think of the cannon and the powder and the cannonball. The cannon is the constraint boundary condition. When the powder explodes, it can't go out as a spherical wave. So it goes down the bore and it blasts out the cannonball and does work on the cannonball. So you get the conclusion, no constraint on the release of energy, no work. That's true.
Right.
But the constraints on the release of energy are boundary conditions, and Newton doesn't tell us where the boundary conditions comes from. Next, where did the cannon come from? It took work to make the cannon.
Yeah.
We can conclude work can construct objects that can be boundary condition constraints, like the cannon. I got that far in my book Investigations, and I got stuck for 15 years. I really did. I couldn't figure out what to do. Matteo and Mile have answered it, and it's just, I want to pause and take it in. It's transformative. We want some work, so we better have some non-equilibrium processes. Processes 1, 2, and 3. So we better have some boundary condition constraints, A, B, and C. So I'll just do it slowly. A constrains the release of energy in process 1, and it constructs a B. B constrains the release of energy in process 2, and it constructs a C. C constrains the release of energy in process 3, and it constructs an A. This is a constraint closed system, and I want to pause over it. It's just magical. I heard about it in 2015, and I said that changes everything. This is a set of non-equilibrium processes constrained by a set of boundary conditions. The boundary conditions constrain the release of energy to do the work to construct the very same boundary conditions. Isn't that amazing? I saw that and I said, it took me forever to realize that my autocatalytic sets do exactly that. So for 15 years, I just was too dumb to see it. But you can see it in Gonen's set. So now let's look at it. Let me define again a Kantian whole. The parts exist for and by means of the whole. So we're all Kantian wholes. I exist because I got a liver and a kidney and a heart and a bunch of genes. So do you. But the parts exist because they're part of us. So that's the Kantian whole. The whole exists by means of the parts, and vice versa. We are Kantian wholes. But a rock isn't a Kantian whole. Okay? The atoms in a crystal exist if they're not in the crystal. The grains exist if they're not in the rock. So lots of complex things aren't Kantian wholes. It's very special. And Kantian wholes are necessarily going to be non-equilibrium systems. So Gonen's set has the following properties. Each of the peptides catalyzes the formation of the next peptide around the cycle. 1, 2, 3, 4, 5, and then 9 makes 1. In each step, the peptide is a boundary condition, constraint, when it ligates the next two peptides on the release of energy that constructs the next peptide, and work is done and a peptide bond is formed. So it's really true that Gonen-Ashkenazi's peptide set achieves constraint closure, and it achieves catalytic closure. All the reactions that need catalysis are done within the set. I'm going to propose that as a sufficient definition of life. It's a Kantian whole that achieves constraint closure and catalytic closure, and you better put it in a membrane so it doesn't diffuse all over the place. Now, pause and take this in. It's perfectly physical, everybody. We just didn't realize it. I mean, I got as far as saying, where did the cannon come from? Okay, in investigating, then I didn't know what to do. Eric and Mile have given us an entirely new notion. I think it is precisely the mysterious élan vital. This is the vital force. Gonen's set constructs itself. Automobiles have the constrained release of energy, right? The gas explodes and the wheels turn, but it doesn't construct its own boundary conditions, like how the gears go together. Cells do. Gonin set does. So already this is huge. Then there's a bunch of other funny things I'm going to tell you. We're all interested in information. I'm going to tell you something because what I tell you is correct, and I don't know what to do with it. So think of Gonin set.
But
Now, let me just say this, because of constraint closure, the constraint closure means that the non-equilibrium processes construct exactly the same constraints. The autocatalytic set specifically constructs itself, right? Now hold that, because that's new to us. Now think of von Neumann's universal constructor. Well, it's cool. It's the generalization of a universal Turing machine. And it's this cool constructor that can construct anything. And it's called U. But for it to construct anything specific, it's got to have some instructions called I. And you stick the I instructions inside of the universe so it can construct something specific. I has magical dual use. I is a physical system that instructs the universal constructor to construct something, in this case, another U. Then I is an object that is copied and placed, the second copy is placed in U. That's von Neumann's system, right? It's entirely different than Gonin's autocatalytic set. The universal constructor can construct anything with the dual use I, where I is a structure that specifies something else. I specifies something else. It could be anything. It's a universal constructor. There's no such thing in Gonin's set. Because of constraint closure, it only makes itself.
Yeah, that's the problem.
But no, but isn't it interesting,
No,
Eric?
that's what you have to unify von Neumann and the Gonin set.
Yeah, you've gotten to where I'm puzzled now, Eric. So let me get 4 steps forward.
You have to unify the two.
Yeah, and the question is, what do we do to do that? That's what I want
I've
to
been
throw
thinking
out.
about that.
Yeah, so I've got a little further. Think of the emergence of the genetic code. Well, that's coding. I mean, you got a sequence of nucleotides, and it specifies now all possible encoded proteins. So it's an amazing jump in evolution, and it can build all kinds of things, but they're all encoded proteins. I mean, it can't make battleships, right? Whereas von Neumann systems can make anything. So von Neumann system is the ultimate freedom. Now just hold that.
Wait a minute. You can also make almost anything in terms of different types of embryos.
No.
Yeah.
Oh. Well, no, hang on. It is true that's fair, Eric. If you evolve piecemeal a set of genes that progressively make evolving embryos, it works out to happen in evolution. But if you throw in random DNA sequences, it's lethal. Right? So there's something funny going on. A lot's constructible. In some sense, the biosphere. But most of the shit would just be dead. Von Neumann's machine doesn't die, right? So you're right. You can make all these organisms. We're kind of leaving out the cell in its role, but that's right. Now, that's really interesting. It's true. Meanwhile, I'm so confused about this. So let's think about information processing. And I've got a Mondrian painting on the wall. And I break it up into 1,000,000 little pixels, 1,000 by 1,000, which I record the intensity of the whatever the dominant color is. So I've got a million pixels that I record each color, in an 8-bit symbol. So 8 million symbols is my description of and representation of the Mondrian painting. Well, who gives a damn? Well, what's neat about it is I can record it on a tape, and I can send it to a machine in Okinawa, and they can print it out, and it's an image that's pretty much like the Mondrian. But I could have sent it to Chicago and a different machine using different ink and different gear cams and a different kind of metal, and printed out the same picture. So what's weird?
You know Putman, Hilary Putman, right? The functional.
Yeah.
State.
What did Putman say about this?
Yeah. Huh?
Well, let me get my confusion out, then help me, Eric. So this is a long way away from Gonin's set. it's way beyond the code that can evolve to make all the embryos that you said, but could kill an awful lot of things.
Yeah.
So what's going on? I don't even know how to say. There's something going on that is construction, and constraint closure is some exquisite case of it, which is
Yeah, I think,
self-construction.
like I said, I think you have to combine the two. You have to combine the constraints with the von Neumann idea. Then when you combine the two, then you can get the generativity plus the constraints.
Please, well, let me go a couple of moments forward, then please help, Eric. We're wondering about what's information, right? And we have the notion of Shannon and Shannon bits and entropy in a real entropy system. And if it's less than maximum entropy, you can get some work out of the system if it's a thermodynamic system. And Paul Davis is wondering, how do we get any causal effect out of information? And he doesn't see how to do it. At least that's what he says. Here's another notion of information. It's a boundary condition. A boundary condition defines the phase space, and a boundary condition specifies what work can get done, but the work that can get done is surely having a physical effect. It constructs a peptide bond, okay? So there's somehow two notions of information that we haven't disentangled. One is something where there's less than maximum entropy in the Shannon system can get used to do something. That's like less than maximum entropy in a heat engine, so it can do some work. But doing work is one thing, but the other thing is the boundary conditions that define the phase space in which the work gets done. We've ignored the boundary conditions in which the work gets done, and that's
So
what
we've ignored the construction of the phase space there too. I mean, that's the crucial thing. One of the crucial things. One of the crucial things.
It's one of the crucial things. The crucial thing the constraint closure gives you is the system's constructing its own phase space and doing work to construct it, which is magical.
Yeah.
But meanwhile, when we think of information as this low entropic state, if it makes any physical sense, it's that the gas could still expand. That's the work part, the energy part, but it doesn't tell you what the shape of the cannon is, right? Yeah. So another notion of information or companion to it is the constraints that specify the phase space.
Yeah.
And that work can be done to change the phase space, like building the cannon or making the autocatalytic set. So I'm lost in von Neumann, how it is in the Newtonian world that it can really be true that we can take the pixels from Mondrian and honest to God, we can send it over to some wires and print it out in type A. How can that be true? How can it be true in the Newtonian world of deterministic physics, and now you're free to throw in some quantum mechanics? How could it possibly be true that we can actually do the pixels and send it to a printer in Taipei, but we could also send it to a thing in Calgary on a different machine and get out pretty much the same picture? And we do it all the time. What's going on in the world that could be true? See, if you say, here's one more.
That's a different question.
Well, it is, Eric. Somehow, if we assume we have responsible free will, it's easy. We just designed it and built it.
I mean, we could also send the genome of a given person to another place in the world, put it into an oocyte, and grow an embryo.
With luck. If you put the genome into
but I mean, the same point. You get the same point. You can get a clone of an embryo by sending it to China, and there you go. So,
well, yeah, hang on. So let's explore it, Eric. So there's a sense in which information is held to be platform independent.
Yeah.
Does that yet bring in the boundary condition that allows specific work to be done?
No, you have to have instantiation.
Yeah.
Abstract theory, instantiation. That gives you the boundary conditions.
Yeah, once you instantiate it in a machine.
Yeah.
But there's a wide range of things you could do to have a machine that will print out the Mondrian painting. And if you put the human DNA in a duck egg, you won't get much. No, you won't.
Right.
Because
Sorry, Stuart. I am very interested more in the thermodynamic aspects in how these ideas were applied to transition in economy, because I think the diversification of economic space, the technological process, Western countries, how the criticality can be observed in different historical processes after the Industrial Revolution. I think your ideas were quite exciting for, let's say, for economic transformation of societies.
there is evidence. Let me try to make the connection. In a critical network, there's the size distribution of avalanches is a power law. Okay? You get a lot of little avalanches and a bunch of big ones. It turns out if you look at Schumpeterian gales of creative destruction, they're also a power law. And some years ago, Stefan Turner, Rudy Hanel, and I made a model in which you get a power law distribution of Schumpeterian gales of destruction. And as I remember, we get a slope of minus 1.3 or something. And that's the actual observed slope in Schumpeterian gales of creative destruction, which you've never commented on. It may be the case that the evolving economy is critical, and the evolving biosphere might be critical. And that starts to look maybe like self-organized criticality. That part of the story is something like this. And I know how to test it. We know a cell is critical. Suppose we take a fungal microbial community. Is the community dynamically critical? We're doing an experiment now that will allow us to answer that. We're taking 70 fungal species and 70 bacterial species with Jan Dijkstra's that have never lived together. We're going to mix them together and plate them out in sterilized soil and watch them for a couple of years. And we're going to see lots of things. So we could ask of that system, when the community is established, is it dynamically critical? There's grounds with some people in Spain, Hidalgo. I can get you the name more. Roughly the idea is the following. A critical system is poised between order and chaos. So it could do the most diverse things, but it's ordered so it's not chaotic, so it can accumulate successes. Well, years ago, I asked, are these things the best for everything? And I discovered no. It depends if a critical system is playing a game against a chaotic system. And I got stuck. I now begin to think that if everybody is critical, collectively we can do the most complicated stuff together. So it becomes relevant to ask, is a mixed fungal microbial community 3 billion years later generically critical? So all the cells are critical with one another because they can jointly do the most complex things. And if that were right, they have an economy. I mean, the human economy is an expression of the economy of the fungi and bacteria. So I fell in love with it. We're two bacteria. I have a flat stomach. I afford you a highway to crawl over and get some food. Well, that's like catalysis, right? Catalysis just speeds things up. So I think I'm thinking now we get collective affordance sets of ways of making a living with one another in communities. And if we do, it sounds like it might be a neat idea to be critical at the same time. And nobody's ever looked at experiments where you take lots and lots of species that haven't seen one another, and you ask, do you co-evolve to criticality? And how do you make livings with one another? So we think we can do that. And what's fun, Andrea Rowley and I wrote a paper called A Third Transition in Science, in which we claim to have proven we cannot deduce what's going to happen in such a system. And the reason is Darwinian pre-adaptations. Let me just say that part cleanly. Let me say this cleanly because it bears on open-ended evolution in computational systems that we also are interested in. An organism is a Kantian whole. The parts exist formed by means of the whole. We have a non-circular definition of the function of a part. It's that subset of its causal properties that sustains the whole. The function of your heart is to pump blood, not jiggle water in your pericardial sac. But that means that the same part has myriad subsets of causal properties, and any one of those could become the function of the heart. So these are Darwinian pre-adaptations, or Gould and Verba's exaptations, and they happen all the time in evolution. Evolution repurposes the same thing for a different use. Flight feathers evolved and were repurposed out of thermoregulation spines in fungi. The transparent crystallines in your eye evolved from perfectly normal colored proteins. I'll hit you with my favorite example. Some fish have a swim bladder. The ratio of air and water tunes neutral buoyancy in the water column. The theory is they evolved out of lungfish, and water got into some lungs, and the thing's poised to become a swim bladder.
Yeah.
And it did. So a new function arose in the evolution of the biosphere by this Darwinian pre-adaptation. And now let's ask, can you deduce it? Can you deduce these pre-adaptive steps? And my claim is you can't. So here's our argument. From one use of an object, say a lung, can you deduce another? So Andre and I are in love with engine blocks. So you could take an engine block and drill 8 holes and make an engine. But you can also take an engine block and notice that its corners are rigid and sharp. So you can crack open a coconut against the corners. It took a while to figure that one out. The point is the following. If you're using an engine block to make engines, you cannot deduce from that statement, I can use this thing to crack open coconuts. That's jury rigging, it's insight, and it's non-deductive. In fact, you can also use the engine block as a chassis for a tractor. That was an inventive discovery. So here's an important step. If we agree you cannot deduce that, and Darwinian...
Well, the trick is you're using the word deduce. There's a different way of looking at it in terms of possibilities, like which you yourself have talked about.
Yeah, go ahead.
No, go ahead. Yeah.
Well, let's ask if you can deduce it. Then let's come to possibility, okay? If you cannot deduce it, the implication is that the evolution of the biosphere is not deducible, which means it's entailed by no law.
Well, it better not be deducible.
Well, it isn't.
Yeah.
But physicists don't like that very much. They want a theory. It also means the evolution of technology isn't. But now you come to possible. Okay, so let's try that, Eric. To have a notion of possible, you have to know what the sample space is.
You have to know the phase space too.
Yeah. No, the same thing, Eric. So if I flip a coin 100 times, I don't know what will happen, but I know all the possibilities. It's 2 to the 100th. So the question becomes, can you list all the uses of an engine block? And you can't. So you cannot list all these of an engine block alone or with other things.
Do you think it's because of the combinatorial explosion?
No,
no. I will tell you, you can do a combinatory. But
let me put something, please, Stuart, because I think when you try to deduce from the uses of the engine block, actually you are supposing an agent or a community of agents.
You are.
And you are communicating between them, among them.
You're exactly right.
Yeah, but then when you change the means of communication among agents, you get really explosions of creativity of new functions. It's what's happening now in our societies. There's a new means of communication, and everything is repurposing new uses, new collective or new individualistic, etc. Then I think that in your view, the idea of communicating agents by real means of communication are the game changers.
Well, I love that. I agree. You're adding to. Well, I was almost there this morning, and it's sitting in Wittgenstein. So the use of something depends upon the agent, what the agent wants to do, and the means that the agent has to do it. For example, if it was a bunch of mice with an engine block, they probably crap on it or something. But I know what the mice are using my parked car for. They're living in it. Okay. There it snowed and the mice are in the car because it's slightly warmer because I don't have because my battery is dead. So this is Gibson's idea of an affordance. A horizontal surface affords me a place to sit, is a triadic relationship between an I, a for whom, a goal, and a possible way of getting there. The affordance is a way of getting there. It's not an independent degree of freedom of the world like position of momentum. And you can't list all the uses of an engine block and for whom. You also can't list all the uses of a screwdriver. Agreed?
Unknown caller.
Unknown caller. Let me just, so this is going to leave in one sentence to what about set theory? Hang on. I'm just going to put it. Anyway, look, it took, so Andre and I were wondering, well, what about this axiom of choice? So we took a move and we looked at the first axiom of set theory. It's the axiom of extensionality, which says two sets are identical.
Unknown caller.
The axiom of extensionality says two sets are identical if and only if they have the same members. Well, we cannot prove that the unlistable uses of a screwdriver are identical to the unlistable uses of an engine block because we can't list them all. We can prove they're different, but we can't prove they're identical. So we don't have the axiom of extensionality. So
you have to go to the axiom of comprehension.
What's the axiom of comprehension? That we just grok it?
That when you have a certain property, it generates a particular set. That, I mean, I'm just expressing it vaguely. I don't have it right now in my notes, but yeah, it's a way of getting around the axiom of extensionality.
Wow. How do you do it, Eric?
Huh? I studied mathematics.
Well, what's the answer? Well, let me go on with my gig, then come defeat me. So you also can't get the axiom of choice. Well, the different uses of things are just a nominal scale. They're not any kind of ordering. And therefore, we don't have a well ordering. So let's try to get a number. For Russell, the number 1 is a set of all things that have a single member. That's a set of all things that have a single use. Well, we can't do that. We also can't get it for 4 uses, right? Because the number of uses is indefinite or unknown. And we can't get it for 0. So on Russell, we can't get numbers, including 0. On piano, we can't get 0, and he needs a successor relationship, but the uses of things are unordered. So I don't have a successor relationship. It seems like we can't use set theory with respect to the evolution of novel phenotypes, novel adaptations, and the evolution of the biosphere. And I'm having a hard time getting anybody to really pay attention to this. So I'm glad we're listening. I can tell you that no physicist will pay attention to it. They won't engage in it. And the reason is, if this is right, when we went from classical physics to quantum physics, we gave up commutativity, right? And that blew away classical physics because of the uncertainty relationship. We seem to be unable to use set theory with respect to deducing the new evolutions in the evolving biosphere, because the biosphere keeps evolving new phase spaces. Can't deduce what's in the phase space. Since we don't know what the We don't know the sample space of the process. We don't even have a probability measure. So we can't find random. We can't measure risk. It's 90 and uncertainty. I mean, you guys, what's happening is this paper's been out for a year and a half. I guess it's an amusing story. Forbes approached me 9 months ago to write about, me and my science. I was very flattered. 17 physicists have refused to engage. They refused.
17.
Yeah.
Wow.
Well, it's a
That's an
prime
odd
number. It could have been 16. At least it's a prime. Well, they're not all physicists. Some of them are, I don't know, whatever. So, and no computational scientists won't look into it. But this bears on open-ended evolution. So,
Yeah, I think you've really got something there with this phase space stuff, this unknown phase space. Very interesting.
It's huge, Eric.
Yeah.
It says that the evolving, in the Newtonian paradigm, we have to identify the relevant variables.
You think that quantum mechanics also has a known phase space in effect, doesn't it?
Sure.
Yeah, so that's a problem.
No. Quantum mechanics is still in the Newtonian paradigm.
Yeah.
You specify the phase space with infinite potential boundaries.
Exactly.
And you integrate Schrodinger's equation to get an entailed evolution of a probability distribution. Then we argue about what measurement is. But you know the sample space of all the the eigenspectrum, right? So you can have a probability measure.
Yeah.
Well, you can't for the evolving.
So the many worlds interpretation of quantum mechanics, what do you think? Does that get there a little bit or not?
Oh, you mean the Everettian interpretation?
Yeah. Because there you have
Everettian
an explosion of possibilities. Have you thought about that?
Well, you've got an explosion of possibilities.
But every universe will quote.
No, this is different. Every time. See, let me see what you guys think. So you got the wave function and it branches because something actualizes. At that instant, all the other amplitudes change in a well-defined way. So you have a flowering of.
Yeah, well-defined phase spaces.
It's well-defined phase spaces at every step, right? Because you have well-defined amplitudes at every step.
Excuse me, Plamen. I think we are over the timing. Maybe if you would like to make some conclusions.
Oh yes, we actually, for me, the view is that we began with Warren McCulloch and his models, his ingenuity in working so many disciplines, and what actually I was curious to learn how Stu was influenced by him, and what we have heard until now was actually the presence of an idea that emerged at that time, and it's still occupying Stu right now, and it is still not. I mean, he's still asking the same question, which is appears unsolved, and I think that we have to continue this discussion. I mean,
I'd like to have Stu talk again. That would be great.
Well, do we have another 5 minutes now?
Yeah, sure.
Yeah, we need more time than 5 minutes, Stu.
Yeah. 5 minutes.
Well, no, I would be glad that we all talk again and it became a conversation. But if you let me go on for a few more minutes, it's what I emailed you guys. So let me try to do it in an orderly way. So we have Hegel being utterly mysterious, and logical atomism comes along to try to get rid of garbage because it's metaphysical. And I did that at Oxford, so I know this stuff. Here's the premise of logical positivism. Ready? Only those statements that are empirically verifiable are meaningful. But that statement itself is not empirically verifiable. The founding statement of logical positivism vitiates its claims. It's not so surprising it ran into problems. How could it possibly be true that they didn't notice it? That's it, right?
Well, you know the story about how a guy flipped the finger at Wittgenstein in a train, and that's how he came to late Wittgenstein.
Oh, is that right? That was the flip?
Yeah. He said, "What do you think of this, Wittgenstein? How do you express that in your line?"
That's great. No, I love this story. Okay, but so anyway, look, this is so Wittgenstein got us to language games.
Yeah.
The Tractatus ends with Wittgenstein saying, "What you can't talk about, shut up." Okay, And that's going to be the problem with getting general AI and open-ended evolution.
Yeah, I was hoping we're going to get to AI, but I don't think we have time. We have to postpone that to another meeting.
But here's its outline. McCulloch gets us to AI. The on-off states of McCulloch's thing are true or false sense data statement. Now get to Wittgenstein and non-reducible language games, right? You cannot reduce the statement, Joe was found guilty of murder, to a bunch of descriptions of people or point particles. So his point is we just invent different concepts, and the different concepts cannot be reduced to one another, which is pretty much like Kuhn and paradigm changes. And I got stuck, I'll just say it fast. I had my Boolean nets, and Jack Cowan and I were going to write a paper saying, just change these things to neurons instead of genes. And so now it's going to be a neural network with feedback loops. And the attractors were going to be the classes, and the basis of attraction were going to be the catchment categories, the content addressable memories. We had the paper drafted. This is something like 1970. And I said, Jack, I don't know how to deal with the Wittgensteinian language games. How do you get from one language game to another? It's not computable. You can't reduce it. You can't compute from one language game to another. If you could, it would be reducible. And I said, the whole thing's got to be bullshit. So we didn't publish the paper.
So that was the reason. That was the reason why you didn't publish it. Okay.
Absolutely, Plamen. I said this just was
Okay.
never work.
I think Jorge has technical reasons to close our session pretty soon.
Let me introduce another meeting, say in a week, perhaps. How about that? So if
let's think about Plamen. I mean, let's think about.
Okay.
I mean, we have to make some plans, step by step and quietly.
Because I would be very much up for it, but I would particularly appreciate that it then becomes a general discussion.
Yeah,
it's going to lead into open-ended evolution and the fact that AI, artificial life, hasn't achieved it. It's going to lead into general AI. It has never done it. I don't think it's going to. It can't do language games. There's something profound going on about systems that can create phase spaces on their own that cannot be deduced from prior phase spaces. And I don't think syntactic computational systems can do that because it wants to derive everything algorithmically. But maybe you can. Life is doing it. Life is doing open-ended evolution.
Yeah.
Let's understand how it does it. It's not algorithmic. Darwinian pre-adaptations are not deducible. They're different uses of the same physical object.
Okay. It is.
And then we can try to see.
Stuart, it is a great complete statement.
Thank you, Stu. Thank you, everybody, for attending this meeting. So let's continue next time.
Plamen, would you organize it so it becomes a developing conversation? We can see where we may want to take it. And you guys may disagree with 90% of what I said, and that's fine. It's a conversation.
Yeah, absolutely. Thank you, Stu, again. And let's see what will come next. So,
meanwhile,
have a nice evening.
Meanwhile, Trump won.
Okay, thank you.
Okay, bye-bye.
Bye-bye.
Bye-bye to everybody.
Okay, bye.
Bye-bye.
Bye.